recurrent neural networks. So Zhang, 15 minutes from now. Thank you. Zhang, you're muted.
Right. Okay. Thanks for the introduction. And I'm glad to present our work. The title is EdgeDRNN, Enabling Low Latency Recurrent Neural Network Edge Inference. This work is done by the University of Zurich and ETH Zurich in collaboration with the University of Sevilla. So I'd like to start with the motivation of our work, which is to accelerate gated RNNs at the very edge. Classic gated RNNs include long short-term memory and gated recurrent unit. They are useful in temporal sequence processing and widely used in speech recognition and machine translation, exemplified by the famous products from big companies. However, the computation is usually on cloud. But in many scenarios, we might want to have edge inference, which is immune to network failure and less privacy issue. However, the edge inference is latency critical and require high batch run performance of the hardware. Examples include on-device speech recognition, human-in-the-loop robot control, and so on. In fact, there are already many previous work on accelerating RNNs with FPGA, and the state-of-the-art one is called BBS. They exploit weight sparsity in LSTM to achieve the highest batch one throughput, which is 2.4 teraops per second. This number is very impressive, but it doesn't show the whole story. The whole system is implemented on the high-end Area 10 FPGA, which has 8.2 megabytes of on-chip memory. And they achieve this number by buffering all the memory, all the network weights on chip. The power is 19 watt, which is too high for edge applications, and the cost is also very high. So will this platform perform well if we just implement it, scaled it down and implement it for edge applications? Let's say we want to run a big network for good accuracy, which has one layer 1024 neurons of LSTM neuron, and it has 6.4 megabytes of dense weights. And we can do 8 times weight compression, and we end up with 0.8 megabytes of weights on chip. However, this number is still too expensive for most edge platforms. So at the end, DRAM is still needed for big networks on the edge, and the performance is still limited by the DRAM bandwidth. So in this work, our target is to design EdgeDRNN to use spiking delta RNN to reduce DRAM access. More specifically, we want to exploit temporal sparsity in GRU, and we want to achieve low latency of running large networks on the edge. We want to make the hardware scalable for any available memory bandwidth, and we want to build this hardware for real-world problems, including classification and control. So we want to implement this hardware on a small edge platform called MiniZ. It has a small FPGA, and the power consumption is only around 2 watts, and the cost is much lower. Now I want to talk about why it's difficult to compute RNNs. So here are the formulations of a simple RNN. As you can see, most of the computations are matrix vector multiplication, where W and U are the weight matrix, and X and H are the activation vectors. The biggest problem of calculating matrix vector multiplication is that you have to fetch very big weight matrix, and that leads to the memory bottleneck. As you can see from the plot on the left, the evolution of memory performance has lagged behind the processor for many years. And in fact, the power consumption of fetching the data from DRAM is up to 1,000 times higher than the actual compute in the chip. So clearly, the critical path of computing RNN is the off-chip memory. Let's say if you want to calculate activation, which is AI, to do that, you have to fetch the activation from the previous layer, which is AJ, and also the weight connections, WIJ. Usually the state vector is relatively small, and you can buffer that on chip. But for the bit weight matrix, in most of the time, especially on the edge, we have to rely on the expensive DRAM. Thus, this is the critical path of the computation. And our solution to this is to exploit temporal sparsity. And the principle is to convert dense matrix dense vector multiplication to dense matrix sparse vector multiplication. Thus, we introduce the delta network to simulate spiking neurons. So instead of multiplying the dense state vector with the dense matrix, instead, we compute the difference between the activation vectors in neighboring time steps, and we get a delta vector. Then we can set a spike threshold. Let's say it equals to 3. So if the delta vector is larger than this threshold, we just keep this delta. And if it's smaller than this threshold, we just make it 0. In this way, we can make this delta vector very sparse, and we can skip the zeros in the sparse in the 0 elements and save computations and memory access at the same time. This figure illustrates this idea. In such a network, we only compute the above threshold computations to save computation and also memory access. And that leads to the design of our accelerator, which has configurable numbers of PE to match the available memory bandwidth. And we have a delta unit inside the accelerator to exploit temporal sparsity and send only non-zero elements to the processing elements. And the delta unit also generates column pointers to tell the memory controller to only fetch valid weight columns to save memory access. As for experimental setup, we implement the hardware on the Minidat development board, which has the smallest Zinc system on chip. It has a single-core ARM Cortex-A9 CPU, small RTX-7 FPGA, and only 0.2 megabytes on-chip memory, and also 512 megabytes DRAM. As for the accelerator itself, we configure it to have 8 PEs to match the available DRAM bandwidth. And we set the activation precision and the weight precision to respectively 16-bit and 8-bit fixed point numbers. We use an AXI DMA IP to manage the I/O, and also an AXI data mover to manage the weight access. As for the power estimation, we use the Xilinx power analyzer. And this table shows the utilization of the hardware. As you can see, the design is very small. As for the low utilization of DSPs, the reason is that we only use 8 PEs to match the available DRAM bandwidth on the board. More PEs brings no benefit for real-time applications. When on-chip DRAM is too small to store big network parameters and can only be stored in off-chip DRAM. Now I want to talk about the network training. For the dataset, we use TI digits, which has audio tracks of spoken digits, and the sample rate is 20 kilohertz. As for the framing, as illustrated in this plot, we use 25 milliseconds frame size and 10 milliseconds stride. As for the feature, we use 40-dimensional log filter bank. The process includes Hamming window, FFT, power spectrum, mel-scaled triangular filters. As for the metric of the network performance, we use word error rate on the whole test set. All the test features are calculated offline on PC and streamed to the accelerator during the testing. As for the training of the network, we train Delta GRU network of various size, and the biggest one has 2 layers and 768 neurons per layer. And during the training, the network parameters and also the activations are quantized to the same precision as the hardware. And now I want to show the performance and accuracy result of the hardware on the largest network, which has 5.4 megabytes of parameter. This plot shows the throughput and also the word error rate versus the delta threshold. As you can see, both the throughput and the word error rate increases with the delta threshold. But we can find an optimal point where we can achieve good throughput with negligible accuracy loss. And thanks to the delta network, we can achieve 92% temporal sparsity, and that leads to 10 times speed up versus the theoretical peak throughput of the hardware. And we achieve 20 gobs per second throughput at this point. And moreover, the delta threshold also has another benefit, which is to allow instantaneous trade-off of latency versus accuracy. And it is really useful for real-time applications. This plot shows the power breakdown of the hardware. As you can see, the EdgeDRNN core logic consumes only 87 milliwatt. It corresponds to 232 gobs per second per watt core power efficiency with 20.2 gobs per second batch run throughput. Moreover, you can see that accessing off-chip DRAM is expensive, even with Delta, consuming 4 times more power than the accelerator itself. However, using Delta leads to 10 times speed up. In this slide, we compare EdgeDRNN with other FPGA platforms. As we discussed before, the BBS was not designed for edge applications. Thus, we assume that the BBS is implemented on the same platform, MiniZ, as we did, and we normalize the performance number. And we do the same thing for ESE, which is another important work in this field. And as you can see, comparing to other work, EdgeDRNN has the lowest cost and also the highest efficiency on the edge. It is 1.7 times higher than the ESE and 2.2 times over the BBS. Now we compare EdgeDRNN to other commercial chips. And in this plot, we show the network latency per frame in a 2.6-second test sample. And we compare EdgeDRNN with Jetson Nano, Jetson TX2, and also a GTX 1080. All the platforms are evaluated by running the same network, and the network on all platforms use features from the same test sample. As you can see, the latency of EdgeDRNN is obviously lower than the Jetson Nano and the Jetson TX2, and is comparable to a GTX 1080 in this specific task. This table shows more specific numbers. If we compare the cost, the power, and the latency, you can see that the EdgeDRNN has relatively low cost with 6 times lower latency and 5 times higher efficiency versus other edge platforms. So to conclude, in this work, we proposed EdgeDRNN accelerator that achieves sub-millisecond inference of large multilayer RNNs. We implemented spiking RNNs that leads to 10 times speed up over normal RNNs with negligible accuracy loss. And it is suitable for latency critical real-world applications on the very edge. For future work, dynamic trade-off of accuracy versus latency with delta threshold could be studied to find optimal values faster. Multiple EdgeDRNN modules can also be instantiated in single FPGA to support batch inference, which can be useful for specific tasks such as multi-microphone signal processing. And another future work is actually to build a demonstration, and we have already finished that by using EdgeDRNN in a real-time processes control. And this work has been published in ICRA 2020. As you can see, thanks to the small size and the low power of the EdgeDRNN, we can attach the board to the processes to do a real-time end-to-end control. At the end, I would like to thank all the sponsors, including Samsung and the Swiss National Science Foundation. And also, I want to thank all the members in our group, the Sensors group in INI. And that ends my talk. Thank you.
Thank you very much. That was